Alright, so for this particular problem, in example number 1, we did the other day that the mean of the cars was 1.1, standard deviation of the cars was 0.943, the mean of the SUVs was 0.7, and the standard deviation of the SUVs was 0.640. And so in part A, what is the mean of the vehicles? 1.1 plus 0.7 turned out to be 1.8 vehicles. And for the standard deviation of the vehicles, we used our new formula, which was 0.943 squared plus 0.640 squared, which turns out to be 1.13. Letter C, what is the mean of the standard deviation for vehicles for 5 days? So I'm going to call this sigma for 5 days. And what I'm going to do is I'm going to take 1.13 squared plus 1.13 squared plus, and we're going to have, I'll just write them out, 3 squared plus 1.13 squared plus 1.13 squared, because when we have these days, each day adds to the standard deviation. So if you don't want to type all that out, there's 5 of them. And so I'm just going to do the square root of 5 times 1.13 squared, which is 2.53. Alright, so in letter D, it says, if Wyndham makes $500 plus $100 per vehicle, how much should Wyndham expect to make in a day? So I'm going to do with the mean. Well, she's selling 1.8 vehicles per day, and she gets $100 per vehicle, plus $500 no matter what, which means 1.8 times 100 plus 500 means that she can expect to make $680 per day. The standard deviation, it didn't ask for it, but we may as well do it. Is just 1.13 times 100, which is 113. And we don't add the 500 because adding and subtracting don't affect standard deviation. Letter E, Linda makes $500 or $300 per car and $500 for SUV. How much money can she expect to make in a day? Well, the mean for this one, she makes $300 per car, so we have to go back all the way to the top and see that it was 1.1 for the car, plus 500 times 0.7 for the SUVs, which gives her $680 again. The standard deviation for this, well, first we'll find a separate standard deviation for the cars and for the SUVs, and then we'll put them together. So for the car, it used to be 0.943, but she's making $300 per car, which means this would be 282.9, and the standard deviation for the SUVs was 0.640 times 500, which is 320. $282.9 squared plus 320 squared turns out to be $427.12 is your standard deviation. So the rules for sums and differences means for standard deviation: the mean of A plus B equals the mean of A plus the mean of B. We talked about this again, but it's not bad to have them written down. If we happen to subtract them, we subtract them. And for the standard deviation of A plus or minus B equals the square root of A, square root of standard deviation of B, add them together in square root. So let's go ahead and try example number 2. Alright, when playing the lottery, there's only two things that can happen. You can win $500, or you can win nothing. So the chance of winning $500 is 1 out of 1,000. And let me change this to be -1 because it costs $1 to play. Didn't say that on there, but it should have. And the chances of losing are 999 out of 1,000. So what is the expected value of your ticket after you buy it? 500 times 1 over 1,000 minus 1 over times 99 over 100. So 500 times 1 over 100 minus 1 times 999 over 100. Sorry, this should be 1,000 and 1,000 and 999. And we'll just round this off to be a nice even. You're supposed to lose 50 cents. Every time you play. And the standard deviation for each time you play would be $500 minus -0.50 times 1 over 1,000, forget the squared, plus -1 minus -50 squared times 999 over 1,000. And that turns out to be 15.82. Alright, so now the question says, what happens? So this is only for one game. So what happens if you play 500 games? Well, the mean for 500 games would be -50 cents times 500. So you would be expected to lose 250. The standard deviation for 500 games would be the square root of 15.82 squared plus 15.82 squared. But we'd have to do that 500 times. So instead of doing it 500 times, I'm just going to do the square root of 500 times 15.82 squared. And so my standard deviation would be $353.75. In example number 3, they give us SAT score for math and verbal score, and we are going to assume independence here, that one score doesn't affect the other, which is probably not true, but let's go with it anyway. The mean is going to be the addition of the two means, so 519 plus 507 turns out to be 1026. Now for the standard deviation between these two, we have to use our formula because these are two separate events. Every time you have a separate event, you have to do the square root of the two events squared, or 3 events squared, or however many events there are. The last one we had 500 events. And so the standard deviation for the SAT is 159.8. Last one, example number 4. Bob has a golf score that is normally distributed of 110 and a standard deviation of 10. So we'll call this Bob. Mean of Bob is 110 and standard deviation is 10. Tom is a better golfer, has a standard mean of 100 and a standard deviation of 8. What is the probability that Bob does better than Ted? Tom. I don't know. So I'm going to rewrite this as Bob minus Tom is less than 0. So the expected value of Bob minus Tom is 110 minus 100, which is 10. And the standard deviation of Bob minus Tom is 10 squared plus 8 squared, and then we square root it, which is 12.8. So they said it was normally distributed for both of these people, so we're going to use a normal distribution. And the mean is 10, and the standard deviation is 8. And we want to figure out less than 0. So here's 0, and here's the shaded region down here. Whenever we do this, we want to find the z-score. 0 minus 8 divided by, let's check that, 0 minus 10 divided by 8. Which equals negative 1.25. For those of you losing the chart, look up the z-score of negative 1.25, and that's your answer. For those using normal CDF, do normal CDF from negative 9999 to negative 1.25, and you should get the answer of 0.1056, which means Bob does better than Tom only 10% of the time, because scoring low in golf is better. Please email me any questions. I will see you tomorrow.